So in this lecture we will go over to lattice energy. We have Na plus and Cl minus ions. It combines to form NaCl solid. Now the energy associated with it can be interpreted in two ways. First, we can say that the energy required for the formation of NaCl solid is called lattice energy. At the same time, we can also say that the energy required to break NaCl solid to form its constituent ions, that is Na plus gas and Cl minus gas, is also called lattice energy. Now at times in questions we would need to compare the values of lattice energy for different ionic compounds, and for that we need to know the variables on which the lattice energy would depend. So here we are, lattice energy would be proportional to the charge on cation and anion and the size of cation and anion. It would be directly proportional to the charge and inversely proportional to the size. Now let us do some questions in which we have to compare the values of the relative values of the lattice energy. Here in the first question the cation is common and the anion is differing. Now we have fluorine, chlorine, bromine and iodine. We have to compare the size. We know clearly that down the group in a periodic table the size increases. Therefore the size of F would be minimum and the size of I would be maximum. And we have read recently that lattice energy is inversely proportional to size. Therefore smaller the size, higher the lattice energy. Therefore the lattice energy would be highest for NaF, followed by NaCl, NaBr and finally NaI. And in the next question we have F common, that is the anion is common and cation is varying. Therefore we can also apply here the relationship that lattice energy is inversely proportional to size, and we know that the size of lithium is minimum, therefore its lattice energy would be maximum, and the size of Cs is maximum, therefore its lattice energy would be minimum. Now as far as the third question is concerned, we see that we have different cation but same anion, but we also see here that the charge is different. In the first two questions the charges were same, that is +1 and -1. Here we see that the charge on Na is +1, Mg is +2 and Al is +3, and we have also learned that charge is always a dominating factor. Therefore the highest charges, that is AlF3, would attract the maximum value of lattice energy. Therefore AlF3 would have the highest lattice energy and NaF would have the minimum lattice energy. And in the next question I think similar explanation can be given for the fourth question, that is lattice energy is directly proportional to charge and charge is a dominating factor. And in the next question also we see that the charge is a dominating factor, +3 and -3 charges are there for both the cations and anions. Therefore Aln would have the maximum lattice energy. Now we have a question, it's a good question actually, and lithium reacts with nitrogen to form nitride while other alkali metals does not react with nitrogen at room temperature on exposure. Why? So we have to explain this. Now we know that whenever a compound is formed we see the overall energy. If the overall energy is negative, that is energy is released, then we say that the formation of the compound is favorable. Now for the formation of nitride we need that N2 should break into its atomic species, and finally we need to add 3 electron to convert it into N3-, which would form nitride. For example Li3N would be a nitride of lithium. Now for the conversion of N2 into N-3, the energy associated would be, first we would need to break N2 into N, that is bond dissociation energy, and next we would need to add 3 electrons to N to form N3-, that is we need to involve EA1 electron affinity 1, 2 and 3. Now adding all these energy we see that the energy is endothermic, no doubt, but after the formation of the compound Li3N, which is an ionic compound, the lattice energy released is so high that the formation of Li3N becomes favorable energetically. On the other hand, due to the larger size of Na+, K+, Rb+ and C+ compared to lithium, the lattice energy is not high enough to compensate for the endothermic nature of the conversion of N2 into N3-. Therefore the explanation. Now let us see here. We have oxygen molecule and we are adding 1 electron to it to get O2-, followed by another electron to get O2 2-, and finally 2 more electrons to O2 4-, which would be basically O2-. This would be called oxide, this would be called peroxide and this would be called superoxide. Now we see that for the formation of oxide we need to add a total of 4 electrons starting from O2 molecule, and the formation of peroxide we need to add 2 electrons starting from O2 molecule, and the formation of superoxide we need to add 1 electron starting from O2 molecule. Now here also we need to understand that the small size of lithium would be able to compensate for the energy required to add these many of electrons to O2 molecule. So we have the explanation here, we have the pointer that lithium form oxide in a small amount peroxide, Na form peroxide, KRbCs form superoxide. We can see clearly here that to form superoxide we need to add just 1 electron, therefore a smaller value of lattice energy can do the job. On the other hand, if we look at the formation of oxide, we need to add 4 electrons in all, therefore we need to have a higher value of lattice energy in order to compensate for the higher energy required for the formation of oxide. Therefore we say that since lithium has a higher tendency to compensate for the endothermic reaction since it has a higher lattice energy due to its small size, therefore the formation of oxide would be favorable only in lithium, and some peroxide can also be favorable. Now for sodium we will form peroxide because because 2 electrons are required, and for K, Rb and Cs we can form only superoxide because just 1 electron is required for the formation of superoxide. Now next question is that Mg, you see that delta H for the conversion of Mg solid into Mg2 plus gas is positive, also delta H of conversion of O2 gas into O2 minus gas is positive, but MgO, okay, the formation of MgO is positive. Why? The net enthalpy, the net energy associated with the formation of MgO is negative. The reason is that we have learned just now that we see the final energy, and if the net energy is negative, then that compound is favorable for the formation. Here we see that the lattice energy associated with the formation of MgO with the constituent ions Mg2 plus and O2 minus is very high. Therefore it compensates for the endothermic nature of these two reactions. Now we have a point here that oxidation state of alkali metals is +1 and that of alkaline metals, earth metals, is +2. Now we have to solve these questions. We have to basically identify the anions present in these compounds. So I think these questions are quite obvious. Some of the questions such as NaN3, we see it here +1, this will be -3, 3 minus, okay, hence then N3 minus. Here we see that Ba 2 plus and N -3. -3 into 2 equals to -6 for anions, and +3 into 2 equals to +6 for cations. Like this basically we have to conserve the charges on the cations and anions. Basically the sum of the charges on the cations and anions would be equals to 0, and I think these all questions are quite easy. So let us conclude this lecture at this point, and in next lecture we will go on to oxidation state of p block metal cations.